All right, let's get chapter 13 wrapped up by going over some of the questions from today. All right, so this was the first question, and I know that we had done part of it, but let's just kind of review where we were going to start. It's really helpful to keep in mind that we can think of objects going in an orbit, a circular orbit, will be sort of governed by Newton's second law, but where our acceleration is a centripetal acceleration. The force that's keeping the object in that orbit is the force of gravity. So we have two planets here, planet Earth and planet Z, and we're going to use this expression to really help us answer the questions here. So here, the force of gravity, let's just do Earth, we'll have right here, and planet Z, we'll just put right over here. So the force of gravity is big G, the mass of the spacecraft, the mass of the Earth, over the radius of the orbit squared, and this is the mass of the spacecraft, V squared over R. Now, the only thing that's different for planet Z is the mass of planet Z, which is 1/4 of the Earth's mass. So okay, so the first question asks us to compare the accelerations, and the accelerations are V squared over R. And so if we look at those two expressions that we come up with for V squared over R, keeping in mind that the mass of the satellite is going to cancel out, we'll see that the acceleration for planet Z is going to be, the Z is going to be 1/4 of the acceleration for planet Earth because of this 4 right here. And so that allows us to say that these answers right here, A and B, are not the same. And we have to narrow down our choices of answers by getting some information about the period, because that's the second thing that is talked about in these answers. So I mentioned that you could say that the period of the motion is the distance that the planet travels in one orbit divided by its speed. We can rearrange this and write the speed as 2 pi r over the period. So what we're going to do is we're going to take this expression and we're going to put it in here for velocity. And this way we're going to get to see how the objects differ in their period. So if I substitute that in for velocity squared, I have big G, the mass of the Earth over r squared, is equal to 4 pi squared r squared over t squared, that's v squared, over r. All right, so we got a bunch of r's that we have to deal with. There's a r squared here, an r squared here. We can just make this an r, and so we're going to get G me is equal to 4 pi squared r cubed over t squared, and let's rearrange as t squared is equal to 4 pi squared over G mass of the Earth times r cubed. This is a relationship we're going to take a look at later with Kepler's third law. So how are the periods of the two planets going to be different? Well, they're not going to be the same because the mass of the central object, which we did this for Earth, but if we were looking at the period for planet Z, we would put mass of the Earth over 4. So right away we can see that the periods are not going to be the same, and so we can eliminate this answer. But in fact, because when we put for planet Z, we're going to have 4 pi squared G mass of the Earth divided by 4 r cubed, the period is actually going to be bigger for planet Z. So this isn't the answer either, because that actually indicated the period would be smaller for planet Z. So through process of elimination, it turns out that for once the answer that says none of the above is actually the answer. Okay, so now here's another question that's going to deal with these things that we learned about the energy of planets in a circular orbit. So just to remind you, we found that the total energy of a planet in circular orbit, and let's assume that this is for Earth, total energy would be big G, the mass of the spacecraft, the mass of the Earth, over 2r, and sorry, I forgot to say that it was minus. The potential energy is minus big G, mass of the spacecraft, mass of the Earth, over r, and the kinetic energy was actually equal to big G, the mass of the spacecraft, the mass of the Earth, over 2. So, 2r, sorry, forgot about that. So these are all the terms that are going to help us because they want to ask us, like, what's going to happen, what's the difference in these energies when compared to when the spacecraft is around the orbit in planet Z and when it's around the orbit on planet Earth. So the thing that's going to change these values is going to be the mass. So for planet Z, the mass of Z is 1/4 the mass of the Earth. And so that means that the energy is minus G, mass of spacecraft, mass of the Earth, over 4 times 2r is going to be 8r. The potential energy is going to be minus G, mass of the spacecraft, mass of the Earth, over 4r. And the kinetic energy is big G, the mass of the satellite, mass of the Earth, over 8r. And all that I did was I plugged in the fact that the mass of the planet Z was going to be 1/4 of the mass of the Earth. I think sometimes for me, when I'm doing these negative values, it can get a little confusing. So I'm just going to remind myself that in general, the graph of total energy and potential energy basically look like this. And so it helps me, if this is R and this is energy, it helps me just remember like which one's bigger, which one's smaller. So for instance, when I compare, the first thing is comparing the kinetic energies. Those aren't as hard because it's positive, and the planet Z has a bigger denominator, which means the kinetic energy is going to be smaller for planet Z. And so that allows me to get rid of answer A. I know right away that's not right. So what I have to, and also, sorry, D's not right either. Now I got to figure out, is it B or C? So I have to think about the potential energy. So for potential energy for planet Z, the denominator is bigger, which means that, planet Z is more out here, where for the Earth, it's more like here. And so the potential energy for planet Z is actually less negative than it is for the Earth, and so that allows me to choose answer B, becomes my answer. All right? Our next question is a star and planets going around the star. So this one is, we want to compare the speed of the orbit, the speed of a planet in an orbit in a particular around a particular star. Here we basically are comparing the Earth around the Sun, and then another planet around star X. And we're trying to talk about the orbital speed. So again, this is going to be the case where we're going to talk about the force of gravity is equal to the mass times the centripetal acceleration. So for the Earth, it's big G, the mass of the Earth, the mass of the Sun, over r squared is equal to the mass of the Earth, v squared over r. This is where you might have been worried when you read the question, is that it didn't really tell you anything about the planet and how it compared to the Earth, because that's going to cancel out. So if we solve for v, or I'm just going to solve for v squared, I'm going to get big G, the mass of the Sun, over r. If I do this for planet X, the mass of the planet around star X, and see again, it doesn't really matter what that planet was, it really only matters what the central object is, and if we solve for this, v squared is going to be big G times twice the mass of the Sun over r. And so this one is bigger. In fact, it's 2 times bigger. And so that allows us to choose answer A. Okay, so again, here we have a question about 2 planets have equal mass, are in circular orbit around a star, and one of the planets has a smaller radius than the other planet. So the radius of A is less than the radius of B. I'm going to use a lot of the same expressions that I used in the question 13.7, which was not the last one, but the one before, the second question we went through. So I know that the total energy is minus big G, the mass of the star times the mass of the planet divided by 2r. The potential energy is negative G, the mass of the star times the mass of the planet divided by r. And the kinetic energy is big G, mass of the star, mass of the planet divided by 2r. Now if I have RA is less than RB, now I want to compare. So one of the things is the first question basically says that planet A and planet B have the same amount of mechanical energy. Again, I'm just eliminating the answers that don't make sense. Because the energy depends on the radius, this can't be true because they're not at the same radius. So I get rid of that answer. If I'm looking at the kinetic energy, it seems to be the first thing that they start talking about. And because planet A has a smaller radius, when it goes into this expression, it's going to give a bigger value. A smaller denominator will give a bigger value. So the kinetic energy of planet A is bigger. So now that means that those 3 answers there are valid. Okay, so now I have to figure out what also is true. So what about potential energy? So again, this is where the graph is going to come in handy for me, because this is the graph that generally tells me what energy and potential energy look like. Planet A is going to be here, and planet B is going to be here because of the fact that the radius, and this is what the radius is, the horizontal axis, or R, is going to be smaller for planet A than planet B. So the planet A is going to have a smaller amount of potential energy, so this eliminates this choice. Now I have to see between these two, it's going to be which one has more mechanical energy. And while, of course, A has less potential energy, it's also going to have less mechanical energy, again, because it's going to be right here. And so that gives us that it's the third answer. This one is not correct either. Okay, so we did a lot of that through process of elimination, and that's okay. It's okay that we did that. All right, so now I'm just going to quickly go through Kepler's 3 laws of planetary motion. They're they're what we call empirical laws, because basically Kepler figured them out based on the fact that he looked at the data for the observations of the planets and was able to figure out how they moved based on the data, but he didn't know what a physical reason why they would move this way. He couldn't explain it. He just knew it was true. Newton's laws of gravitation were extremely important because they actually were able to explain why the planets moved this way. Okay, so let's talk about what these laws are. Well, the first law basically says that the planets moved in elliptical orbits. That was a big deal because up until that time, everyone assumed that the planets went in circles, and they didn't. And that's why nobody could figure out a grand scheme of how the planets were moving. So the planets actually move in an ellipse, which is a mathematical type of shape that's really important, where it has 2 focal points. Here you have S and S prime shown. The distance from one focal point to the edge of the ellipse and back to the other focal point is constant. So if I actually took a piece of string and tacked it at S and S prime and then held my pencil taut on the string, I could trace out the path of the ellipse. In any case, what happened is that was really important because it meant that the distance of the planet from the sun was not always the same. It would vary during the orbit, and that really affected a lot of other motion of the planet, for instance, the speed that it would travel at different points in its orbit. This also was important to understand because it turns out that while this picture, the orbit's very obviously elliptical, the eccentricity of the ellipse of the planet's orbits, and the eccentricity basically is a numerical way to quantify how elongated the orbits are. The eccentricity for most of our planets is very, very small, which means they're almost circular, but just not quite. And that made figuring this out made it extra difficult. In any case, the first law basically says they do travel in elliptical orbits. The sun is at one of the focal points, and that's the first law. The second law is kind of weird because the way it's stated, it's actually hard to figure out what they're saying until you really think about it, because he said, a line from the sun to a planet sweeps out equal areas in equal times. So basically, these shaded areas are the areas that are being swept out here. And so the idea is if we say this is 60 days and this is 60 days, if we take equal time intervals, these 2 areas have to be the same. Now, when we draw the orbit as being really elliptical, it's very obvious that these areas look very different, but the big difference is that out here, the actual distance in the orbit that the planet covered is so much smaller than over here. And so what we know is that the planet is traveling faster when it's closer to the sun, and it travels slower when it's further away from the sun. And that was the second law, is basically the consequence of the second law makes it a lot easier to understand. Except, if you're not, the wording is just really kind of obtuse. It turns out that this second law is a consequence of the fact that there's no external torque on the planet, because remember when we learned in the last chapter that the torque gives a change in angular momentum? Well, because the force and the radius are parallel to each other, actually anti-parallel, the torque is 0, so the angular momentum is constant. And so the motion of these planets around the sun are very similar to the ice skater who pulls their arms in, and as they pull their arms in, they go faster. The angular momentum of the planet could be the mass of the planet times the radius, the distance of its orbit, times its speed. And so what happens is when the planet gets closer, when radius gets smaller, the velocity gets bigger, and vice versa. It's just conservation of angular momentum. Okay, finally, the third law is the fact that the period of the planets and their distance from the sun, or the semi-major axis, which is the length along the long side of the ellipse, are definitely related. Now, we did this with a circular orbit, and I'm going to do it in a minute, but this relationship here might look somewhat familiar because it's pretty close to the expression for period that I got when I did the first question in this video. So basically it's saying that there's a definite relationship between how far away the planet is from the sun and how long it takes it to go in its orbit. Kepler's law just basically puts it into a quantitative relationship, where this is the period and A is basically the distance from the sun. It's a good approximation. Just sort of remembering how we got this, if we said the force of gravity is equal to the centripetal acceleration times the mass, and we're talking about the mass of the sun, the mass of the planet, r squared, mass of the planet, v squared over r, but we said that the period of the planet, this is how we get the period into it, so we come up with the expression for how I write v in terms of period. Get rid of the mass of the planet, doesn't matter. We have big G, mass of the sun, is equal to 4 pi r cubed over t squared. And I get t squared over here. Sorry, forgot the pi squared. And so, again, if you go back and compare, so we did this derivation for Kepler's third law, but we assumed that the orbit was circular. It makes it a lot easier to do it than when we have to deal with an elliptical orbit. And you'll see that this really basically has exactly the same form as what we were shown when we assumed that the orbit was elliptical. We just replaced the r with the semi-major axis, and you get the exact same expression. So, thinking about that, if we took the sun and we shrunk it to half of its present radius, but it kept the same mass, we want to know what effect it would have on the radius and the period of the Earth's orbit around the sun. Well, we just derived the expression for the period and said that it was 2 pi over the square root of big G times the mass of the sun times r to the 3/2. And so basically, there's nothing here that's going to change. The radius, the period doesn't change, and the radius doesn't change, and so they just completely don't change at all. One last thing, I was kind of talked to one of the groups today about the work done by gravity, and so remember, work done by gravity, as the planet goes around the sun, keeping in mind that the force of gravity is always towards the sun. And we want to think about, like, when is gravity going to do positive work and when will it do negative work? The force of gravity will do positive work as the radius decreases, and it will do negative work, and that's simply because the force of gravity and is in the same direction as the change or the displacement, which is towards the earth, towards the sun. And if you are moving in a time when you're getting further from the sun, you do negative work, and that would be as your radius is increasing. So interestingly enough, that means that as we go from, say, the furthest distance from the sun to the closest, we're going to be doing positive work. And then as we go from back to the furthest place, we do negative work. The total work is always going to be zero because you end up where you started. And so you have no net displacement. But during the orbit itself, it's possible for gravity to be doing either positive work or negative work depending on what kind of displacement you have. All right, so I know that that was kind of quick, but hopefully that gives you a better sense of the very end of the chapter. And on Monday, we'll start with Chapter 15 and simple harmonic motion.